Okay, so folks, just to level set, you should be inside your Vagrant VM. You should be able to type each of these 3 commands, and you should see the following output. If not, it's going to be difficult to do the next step. So first of all, we want to make sure that VPP is not running. So be very clear, VPP should not be running. Next thing is just make sure that we don't have any problems with huge pages before we get going. So cat proc, meminfo, grep huge should look like that. And you should have the IP net namespaces on your system. Now what we're going to show is, and as always, I'm going to do it through Emacs. I have no idea. So the question was, sometimes when he does stop VPP, he still sees multiple VPPs. It's potentially you could have disconnected an SSH session, quit Emacs prematurely, run in the background. Shouldn't normally happen. My suggestion would be just to kill those processes and then make sure that your output, again, looks like this. You have your net namespaces, your huge tables, especially free is not 0. And that the only output of that is the actual grep itself. So rolling along, consistently, we're going to be starting VPP from GDB. So I'm using good, but you folks, as you used in the last session, we're going to keep it consistent. We're going to be running the same debug image. Now, shouldn't have any breakpoints set. We're not going to be using breakpoints for this. Make sure everyone's just up at that point. Haven't started it yet. Okay, no, everyone, generally I'm just waiting for whoa, slow up. If I don't hear that, I'm just assuming everyone's kind of at the same spot. So we've started GDB. We haven't started VPP yet. So are Unix interactive? Now here, you notice I didn't get any blacklisting here. This one is my NAT interface coming in. You'll notice that you should have these guys pop in here, and we should be able to show interface and see the interface, potentially see the PCI interface as being down, and you won't see any AF packet interfaces. So far, this should be fairly consistent for everyone. These are the packet generator interfaces, and we will discuss those in a bit more detail tomorrow. From here, in order to take a can config, so everyone should have downloaded the MacSwap.conf file using wget, and it should have placed it in /vagrant. So to run that, it's EX, as in execute, and we'll treat it like a script. So it's just going to treat these as a bunch of commands that you would normally type in from the command line. So this is a very quick way to put in a bunch of configuration that you would sometimes type in via debug CLI and punch it into the system. So I'm going to do that. I'll give everyone a few seconds to catch up. Everyone good so far? Okay. From here, when we do show interface, we now see that, at least on my system, because the configuration file was set for that particular PCI address, we talked about this a little bit in the last session. If you do LSPCI, you can get the actual address. We turn that PCI address into this gigabit address/address/address type format. And we've added these host VPP commands. So I'm going to go have a quick look at that file, just so people can see what's in it. So here we're creating the host interface with name of VPP1. So that's looking for the AF packet interface we created on the host called VPP1 for that net namespace. Same here, we're going to create a host interface on VPP for the AF packet interface on the host called VPP2. Here I'm just bringing up my particular PCI interface, giving it an address on my VirtualBox network so I can reach it from outside if I need to. I bring up the state of my 2 AF packet interfaces. So notice when I create host interface name VPP1, on VPP, the interface is called host dash the name of the interface. And the IP addresses that correspond to the subnets that we put into those net namespaces we've been using. And this IP probe command, basically make sure that we can reach that address, and we have an ARP entry for it now. So going back, you would have seen here, we've resolved, that's the result of that probe. And indeed, if we now go back and you see these interfaces, you should be able to get to a shell prompt. There's my net namespaces. So from here, I can say for a net namespace, execute within net namespace VPP1. Let's have a look at its IP address. It's in subnet 1/24 with a .2 address. Its gateway peer is .1. And we know that VPP2 is in 2/24. So from here, inside the namespace, we can do a ping, give it some number of packets to count off, and we'll ping the interface inside the other container, which is 16.2.2. So everyone should now be able to ping between the namespaces. So we're not doing any max swapping, we haven't invoked our node yet, we're just pinging straight through VPP. Everyone able to do that? Yes, question. Do you wait for a mic or? To execute the script, it's ex space and then the full path to the file name. So /vagrant/maxswap.conf. Yeah, it has to be full path. Just go full path. To the wiki, you can click on that link and copy paste from the URL. Okay, so now we've been able to ping in between these two things. Let's go back and have a look at some stuff within VPP. So now if I do show error, you can see we have some ARP replies sent, ARP replies received. Now, if we have a look at our, it's a bit difficult to actually, if you do show vlib graph here, and we look for MacSwap. See, MacSwap is saying that the next node for it is interface output, and that as far as interface output is concerned, the MacSwap can send to it, but what we don't see here is anything actually sending to MacSwap because we haven't enabled it at the CLI level. So let's do that now. So pursuant with the debug CLI, it's command ? We could just start with ? From here and hit return. If you want to do show ? In our case, we want to do MacSwap ? So you can see that there's only really one command, enable disable, which allows us to use an interface name. So let's go ahead and enable that. First of all, let's do a trace add AF packet, and we'll go into what this trace command actually is and doing and how you create one of these for your own node tomorrow. But for now, it's suffice to say this is the mechanism by which you can watch a packet's path through the graph node, right? So we're going to say AF packet input, chattering and trying to type at the same time. So we're going to add a trace for AF packet input. Okay, so now anything that goes through that node and the rest of the graph, we're going to capture and see the output for 10 packets. Okay, so we're going to go back. If I do show trace, there are no packets in the buffer. If I go back to my shell, run ping again, show trace. If I go back up, we'll start at the top with packet 1. Okay, so we can see that we had a packet come in on AF packet input. Okay, that would make sense. It had a hardware IF index of 6 and an X index of 1. We're using the tpacket2 header, so you can look inside the, it's a Linux kernel header file, describes that kind of frame format. The next cab off the rank is Ethernet input. So from AF packet input, which is our host AF packet interface, it goes to Ethernet input. It has a look and says, okay, that's IP. We can also see some information here about MAC addresses. IP4 input, so here it is, 172.16.1.2, the interface inside our source namespace. It knows it's ICMP, and it knows it's trying to reach 172.16.2.2. Some other information, type of service, TTL, length, fragments, ICMP, echo request. Then we go to the IP4 rewrite transit, look up some adjacency information. Again, on Thursday, we'll go into a deeper dive into the fib and adjacencies. Dave will go through that for us. And then we go to host VPP2 output, which is the interface output, and it's going to punt it out to here. Remember, host VPP2 is the name of the interface that this sucker, this 2/24 corresponds to, the VPP2 net namespace, and so on and so forth, right? Here we'll see the reply back. And so this is an extremely useful tool when you're trying to troubleshoot what's going on. Now, like all troubleshooting tools, it's only as good as the information it spits out. So these fields in here aren't just created by magic. So when we create our graph node, and this is one of the things we go in tomorrow, is we need to construct what output we are going to put in to our trace. When someone says, I'm going to trace stuff, and it goes through MacSwap, right? And that's one of the exercises we'll go through. So yeah, I'm just using the generic MacSwap skeleton. Let's have a look at enabling MacSwap. We're going to run it. Now, what do you think is going to happen? We're going to be sending a packet from 1.2 to 2.2. That packet's going to come back with the same IP arrangement. The source and destination IP we're not changing, but the MAC address is going to be swapped. Well, it's just going to junk it. So we're not going to expect to see any kind of response. We could try running TCP dump, I guess, but we're not going to see a reply in terms of, yes, acknowledge that's a ICMP echo request. I'm going to send an ICMP reply. It's going to get it and go, this is junk. But using trace, we can actually watch and see what's going on. So we've proven that it pings, right? We've proven that packets are going through VPP. We have a mechanism by which we can see the graph nodes that they're going through. So let's enable our MacSwap feature. So remember, it's MacSwap, question mark. So we'll do MacSwap, enable, disable, and I'm going to do it on host VPP1. So far, so good. I'm going to clear my trace. We trace add AF packet input node 10. So we're going to capture 10 packets and do the same thing again. Now remember, we set it on host VPP1, which means we have to ping from that namespace, VPP1. And as expected, we're not seeing anything. And these will eventually time out. Okay. So we can just look at any one of these traces. It's pretty much going to be the same output. So remember, AF packet input, same node that we had for the last ping example that worked. Same hardware IF index, so that's reassuring. Next index is 2. So before, it was going to Ethernet input, which was next index, I presume, 1. Now it's going to MacSwap, which is next index 2, the next enum, right, in that list of runtime nodes that we want to dispatch to. And there's some information here about len and snap len, so tpacket2 header has that type of information. And here we have MacSwap, and it just spits it out the output, so we're not doing anything fancy in terms of Ethernet input or IP4 lookup. We're just sitting on the interface, get a packet, swap the MACs, spit it back out. Literally what we're doing. Go ahead, mate. An up arrow of the history of the commands I did. Show trace. Trace add AF packet input 10. What was the command to list all the nodes? Vlib, show vlib graph. Okay. So moving right along.
So one question, what I don't get is who's actually sending to this MacSwap node?
So the question was, who is actually sending to this MacSwap? So it's the namespace. So if I was to show, let's have a look at a quick picture, and then we really need to get going through the presentation. So here's the namespace, 1.2 in VPP1, sending to 2.2, coming in on the host. Normally, without enabling MacSwap, it was hitting a node in VPP called Ethernet input, and then just following the normal path. I see you're an IP4 packet. What do I do with it? It's not for me. It's for someone else. Let's look up how to get there. Rewrite transit, because it's a transit packet. So not local.
No,
Now,
I meant in terms of the graph, which is the node that is sending to the MacSwap.
excellent question. Okay, so let's have a quick look at that. So now, if we do show vlib graph, sorry, that's a very good catch. Thanks, Christian. We see that MacSwap is going to send its packets to interface output. That's consistent, but it will receive packets from AF packet input. Now, how that occurs, and we can go into a bit more detail tomorrow, and when we go through the CLI and what that's actually doing in terms of dynamically adding that arc back, is saying for this particular interface, right? Remember, it's MacSwap, enable, disable, particular interface. This is the thing I want to get to, right? So remember, in the types of nodes, we have internal graph nodes, this is one, and we have interface nodes, right, which are handled slightly differently. And we saw when Dave was walking us through before and had me kind of poke inside MacSwap very explicitly the hardware interface, where we're wiring it to the hardware interface. That's a little bit different. And tomorrow we can talk about how to actually wire things to internal graph nodes, but for now, that's the mechanism. But good question, thanks. So let's actually talk about what's going on inside MacSwap. That was the last one we did. We are here. So let's break this down a little bit. So this is the dispatch function for our node, the MacSwap node FN. So if you were to have a look in node.c, right? So it'd be under, if you did it the way the tutorial went, it'd be under /vpp, devboot, MacSwap plugin, MacSwap, node.c. So this is the dispatch function. You'll see that we're getting our vlib main t. Whoops. We're getting our vlib main t, our node runtime, which is us, and a frame. Now, endLeftFrom is a key variable that's going to keep cropping up inside the standard graph node pattern. And all endLeftFrom says is we have work to do and how much. NextIndex is our speculative assignment. So you can see here in the highlighted bit, NextIndex equals the node's cached NextIndex. Now for us, it's very simple. It's going straight back out the other interface. When we actually get through in a bit more detail, walking through the functions, and that's where I'll punt to Dave to talk about what happens though if the next index we really should be going to isn't the last one that we just happen to cache. But for now, this is a presumption that there's, like I think the perfect analogy Dave gave me in the break was, it's like the weather. In lieu of any decent forecast, tomorrow's weather may as well be the same as today's, right?
Yeah,
and
that's about the best default guess you're going to come up with.
Yeah. So here we have what we call a dual loop. First, there is a outer loop. Is there anything at all to do? So while endLeftFrom is greater than 0, meaning we have something to do, let's start doing stuff. Now, vlib get next frame says, look, let's check if our neighbor node, which is ordinally the next index. Remember, if you have a look at show vlib graph, you see the next nodes. There's a list of next nodes, and I have like 0, 1, 2, 3, 4. That's that number there. It's basically saying which number in the next frame, right, do I need to go to? Who's the next node for me? All right, so let's check that that node has space in its frame for us, the node, right? And we pass that to vlib get next frame, right? Do you have enough space for me? We also check some permissions. You may have seen some ownership stuff. That was the first twiddle 0 example I gave. We didn't dive into that too much, but that's where we check. Do I have permissions to write into this frame? Am I allowed to? You can go dig into that yourself by all means. And then on return, right, so from vloop get, you want to inject something, mate? Or I'm going okay?
No,
On
you're
vloop
fine.
get next
I'm just
frame.
checking the slide out.
Yep, on return to next points to where we can write to for the speculative sequence. So when we call that vloop get next frame, to next will be modified. And end left to next is how much we're actually allowed to write there, right? So there's where do we write to for the speculation and how much are we allowed to write. So now we've got two bunches of things to count in terms of what we're allowed to write. There's how much work do we actually have to do, end left from, and there's also end left to next, how much we're actually allowed to go and chuck to the next person based on their frame before we have to allocate another one. So then we start breaking down into the dual loop. And so the dual loop basically says, look, while there's work to do, end left from, and while the end left from is greater than 4, and I can write more than 2 packets, more than or equal to 2 packets to the next graph, let's do 2 packets at a time. So we'll validate the buffer NQ by 2, and so we'll dive into that one in a little bit more detail in a bit. And this is, I believe, Dave, where you dive in when we get to that section on the single loop about how do we fix the next index if it's potentially wrong. He'll go through those cases, and it's actually pretty cool stuff. But you notice we're doing it by 2 because we're handling 2 packets at a time here. And you'll see I snipped a bit of code out. We're going to walk through this in a lot more detail tomorrow when we get soon, right? See how far we get today. We'll go through that, how we're actually handling 2 packets at a time. But essentially, it's duplicating code, right, in terms of our buffers and buffer indexes and the things that we're doing with the max swapping. But this is showing essentially that even though you can duplicate those bunches of code, here we're actually going to enqueue 2 packets. And here I'm saying, remember, we expect the best and prepare for the worst. When we get down to this single loop, right? So this is our cleanup loop, is another way of saying it. So you hear the expression dual loop. These are the 2 loops, these 2 inner while loops. The first one, if we have a chance to handle 2 packets at a time, let's do it. And as soon as there's not 2 packets left, let's just iterate on single packets, right? And that's the cleanup loop.
I mean, the simplest possible case is you have an odd number of packets, and you don't want to be leaving the odd duck out.
Mm-hmm. Yes, exactly so. So next 0 assumes that our next graph node is the output interface. So this is statically coded here. You think of this as what's my default. You can set an intelligent default inside your loop for next 0 to say what's the next graph node I would punt it to by default in the absence of any other information. But then we set our buffer index speculatively enqueued to the next 0. And then we just do some cleanup things in here in terms of adjusting counters to make sure that where our counting is making sense when we jump through the loop. Note that in here when we do end left from, and end left to next, in the single loop, we're decrementing by 1. In the dual loop, that'd obviously be by 2. We've got to make sure we don't have underrun problems, right? Hence why the outer loop has those 2 indices or 2 checks for 2 and 4. Okay. And vloop get buffer gets us our buffer, and then we can actually start doing stuff with the MAC address. So once we get that buffer, or that pointer, or that index to the buffer, then we can actually get this Ethernet, EN0. So EN0 has type Ethernet header T, and that gets a pointer to the return current data that we're allowed to process and manipulate. And so now we can finally start swapping MAC addresses. So we create a temporary variable. Here's a macro actually, and what you'll find this macro does is actually repeats itself 6 times, 6 bytes in a MAC. So for each byte, take a temporary variable, get its source, a byte from the source address, then take a byte from the dest address, and the source address gets that, and then the dest gets the byte from the source address. Simple swapping algorithm with a temporary variable. And if anyone can come up with a better way of doing this, I've seen stuff on, for example, XOR, there's XOR algorithms, and there's some contention as to depending what instruction set you have, whether they're more efficient, less efficient. Yeah. You're talking to the master here, right? So
well,
it depends.
You're talking to the master. On the other hand, this isn't really particularly a hardcore networking function. I mean, MacSwap is just, it's a good sample program, but I'm the lazy so-and-so who kind of did it the obvious, just go swap the bloody bytes. I don't want to hear about this anymore. On the other hand, there are places where really looking at the generated assembly code and measuring it, in the rewriter, how would you put it? There's a case where you're rewriting almost always 14 octets, standard Mac header rewrite, and throwing the packet out interface. And that's one where we've tried to be reasonably careful about it. One of the things that people think of in that space is, oh, gee, well, I can be a little sloppy and actually rewrite 16 octets. But the bear trap there is if you're rewriting, a 14 octet header that starts right at the DMA boundary, you will have prefetched that area. If you creep back 2 octets into the rewrite space, you just blew another cache load, and an unprefetched one. So, you got to be a little careful what you wish for. Just the pure number of apparent clock cycles may not be interesting. At any rate, this is a sample program, and if somebody wants to explain how to do it better, for God's sakes, do it and check it in.
So you've heard Dave mention software IF indexes before. So here is where we're actually setting our software IF index into the received index. So this is how we're actually going to punt it back out. So we set the software IF index equal to the index that we just received it from, and then we flip it back, same structure, VNet buffer B0, pointing at SWIF index sub VLib RX. In this case, we're doing sub VLib TX, and it gets the SWIF index. Pretty simple, just punting it straight back out the way it came.
Yeah.
Other things you can do, for example, this pattern's fairly common, especially with tunnel end caps. You want to get the SWIF index. You have a key, look it up, it'll return the SWIF index for that key, and that'll help you get to the end capper, which again will do its own lookup to get the hardware buffer and send it out the correct interface. Something we can maybe look at Thursday during the hackathon for the any kind of tunnel end capper you like. The one I'm more familiar with is the VXLAN GPE, but they're all pretty much very similar, right?
Yeah, depending on the data structures, we'll go through the buffer metadata in excruciating detail for a period of time when I'll put everyone to sleep. And the thing about it is, one of the obvious questions you might ask yourself is, why isn't this all just the RTM buff data? And in a certain sense, it's a mix of historical accident, doing things slightly differently, and actually having a real network stack that uses the metadata in ways that the RTM buff metadata, could you put stuff into the mbuff private area? Well, guess where all this stuff actually lives. So it's kind of it's even a reasonable player with respect to the DPDK buffer metadata, in that it's private data from that point of view now, specifically so that we can eventually link stuff against the upstreamed DLL version of the DPDK rather than having to build it all the time.
Yeah, okay.
So,
cool.
Sorry, story made long.
No. Then we actually start to enqueue the packet into the pending loop. So our while one loop, one of the things it does is look for pending frames, where to come from, where do I need to send it to, process it. This VLib put next frame enqueues the packet to that. Sends a signal that there are pending frames, go do something with it. And then obviously, very importantly, vnode increment counter. So instrumentation, obviously very important. Are there better ways of doing it? I know Dave's mentioned, sometimes we can tell if a packet's gone through. We don't necessarily have to fire off a counter, especially if it's in a highly used graph node. There might be better ways of doing it. But by and large, always want to be able to see when we get a patch come in for a new feature in a graph node, are you counting things? Are you making sure you're instrumenting what you're doing? Sorry, there was a question. Can you maybe just wait to get a mic, please, mate? Sorry.
I have a generic question, okay, not related to this MacSwap thing. Let's say I have 100 frames coming into a node 0, and node 0 decides 50 frames goes to node 1, 40 frames goes to node 2, and I drop the remaining 10 frames. How do we handle this scenario?
Okay, so you're going to make a decision. If you have the capability of sending to multiple arcs, right? Say, as you said, you want to send half the packets to node 0, half the packets to node 1, and, oh, sorry, that doesn't leave us any to drop.
Yeah,
some
drop
amount to
some
drop,
more.
right?
Drop few packets in that
Right.
node.
So you're going to set up the number of next nodes in your graph, right? You're going to say, when you register, hey, I'm node 0, right? And I have the capability to send to these 3 nodes, right? And I'll name them, right? Whatever name you know them as, right? And remember, in the initialization sequence, we go through and we say, okay, what are the next nodes that I know how to talk to? Remember that vlib node add next by name or add named by slot?
Add next with slot.
Yeah, and the named portion though, where the named variant.
Yeah, well,
Right.
it's a hash lookup, yeah.
Yes,
Same
exactly
diff.
so. Yeah, so it's using that vlib, yeah, thanks Dave, vlib node add next with slot. Remember that I said it's kind of, there's a step that's kind of recursive. It's going to look up that name, right? So that's, in the vlib registration says who it is. Then in your code, right, you're going to have the same enums for the next nodes, and you just know 0, 1, 2, and you reference them by the enum name.
Yeah.
Okay, so you see in vlib, show vlib graph, the nodes I can send to all have that 0, 1, 2, 3. And we can go, I can show you in a bit more detail in another one.
Yeah,
So go ahead.
and in the standard single dual loop, or even in the the fully pipeline model, at some point you're going to set next 0 or next 1, depending if it's in a dual loop. You're going to set that to one of those enum values. You drop the packet in the magic macro, and poof, it goes there. It's really just about that simple. There's a lot of machinery and pay no attention to the man behind the curtain stuff going on. But the bottom line is, you either statically or dynamically create graph arcs. Those will have small numbers starting at 0. You set next 0 to the one you want to push the arc you mean to use, and you drop the packet into the NQ macros. Filament 11 done.
Yeah.
So just a follow-up question on that. So if there are just 10 packets that goes to node 2, like the vector is not full yet. So do you wait for the vector to get full, or you just go through as and when you get?
What ends up happening is at the scheduling level, as soon as you make a frame's what's called a pending frame T. As soon as you make that guy be runnable, you'll end up enqueuing the frame so that it'll be found when the dispatch loop gets there, so that typically there's a reasonable order in which the frames are scheduled. Now, you'll continue to paint into that frame whether it's been scheduled or not, and at the end, at the end of the standard looping, you'll see mumble vlib put frame to node. What that does is it fundamentally it finalizes the count as far as this source is concerned. Now, if 3 other nodes also pour packets into a particular node, which can easily happen depending on what you're doing, in tunnel and cap cases, again, it's a directed graph. It's not an acyclic graph. That it's pretty common to say, okay, IP4 lookup, go find an adjacency that's a tunnel, rewrite, screw around, rewrite it, send the packet back to IP4 lookup. And what that'll do is, it'll make sure that the appropriate set of frames are scheduled to be run by the graph dispatcher. It's an eager algorithm. Before you get back to the top of the while one loop and start looking for more work, you actually completely flush the graph. So another question that comes up in this space is, well, my God, what's going to happen if every packet goes a different way? First of all, it's just about impossible to make that happen with real traffic. In fact, the only way you can get vectors with n equals 1 in them is when processing at 10 pps. You get one packet in, and then it degenerates almost to scalar packet processing. But the good news is you can't be very busy if it's doing that. So yeah, fundamentally it's an eager dispatch algorithm. It always flushes the graph before it looks it looks to the input nodes for more work.
I thought maybe if you don't mind, we could, once this comes up, you could walk us through, I'll pull up the code, the vlib validate buffer enqueue. Just a little bit about, what happens if next 0 is wrong.
Oh, yeah, no
Yeah.
problem. Glad to do that one.
Yeah. Because,
It's just,
packet up, packet. That's the typical one that's going to chuck you, right? Some kind of intermediate packet that you don't really expect in the flow.
Yeah, it's generally speaking, it's duck, 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 goose, duck, 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 goose, something like that. Where if you think about the Ethernet input node, mostly if you're doing IP4 packet, processing, let's say, you're going to get a lot of, ether type 800, 800, 800, and then you're going to get an ARP packet. And you just want to make sure that, by God, the ARP packet goes to ARP input, because you don't, it's not particularly an IP4 packet. Do you want me to?
Yeah, mate, I've got it up here.
Okay, yeah, all right. So now, that's actually not particularly the place I'd start with
So
the
where do you want us to
story.
go to, Matt?
Go to IP4 lookup.
Ah, I see.
Because I want to show the 1 or 2 places that are left around with it open coded.
You can drive.
Okay, yeah.
I haven't got anything magical turned on.
Okay, where? Whoop. You use the real control button here.
Yeah.
Oh, come on, you're such a puss. Right. Okay, where are we? Oh, we're in Vienna. IP. Sorry to be slow, guys. Okay, so now we're going to go search for, let's see. Right. Okay. So now, do folks want to talk about about the dual loop a bit in more detail here? And what you end up doing is just saying, that you've got at least 4 packets free, and that you've got places to process at least 2 of them. So what you do is you end up basically prefetching the buffer header and the first cache line's worth of data, which is going to have the IP4 dest address. That's the prefetch one trip around the track ahead. So you do that, and then you say, okay, fine. Notice that you're doing this game where you say toNext of 0. Now, toNext of 0 is set by the getFrameToNode macro outside of here. In the beginning of time, it says, it's this, let's see, next. Okay, next is the cached value of where have we been putting these guys. And what you're doing right here is you're saying the packets that we're processing now, I'm going to send them speculatively exactly where the last pair of packets went to a first approximation. We'll worry about it later if that doesn't turn out to be where they're going, because in a lot of times IP4 lookup is going to be followed immediately by IP4 rewrite. It might be followed by drop. It might be followed by something way funnier than that. If you hit an IP adjacency that says, oh yeah, this is a tunnel encap case, go see the tunnel encapsulator. But the speculation here is that, again, the weather tomorrow is going to be the same as the weather today. So we go speculatively enqueue those packets forward in the graph where the last pair of them went, and then we yada 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 yada. We fool around. Eventually, assuming it's not anything complicated going on, we get the adjacency, and then we say, okay, next 0 and next 1 is where this pair of packets really goes. With any luck, now we'll do a little more, counting, yada, yada. Now here we get into the interesting thing. Wrong next. Okay, wrong next is a quick calculation to say, okay, next 0 isn't where I just emailed this, or twice next 1 isn't where I emailed this. Because I've already enqueued the guy's sum. In most cases, wrong, we're going to say, okay, I really do believe the weather tomorrow is going to be exactly the same as it was today. So in most cases, you're flat done. If you get packets in a row that are really going the same place in the graph, there's nothing much to do. Howsoever, you might have gotten a case where you have one that's going to A, for IP4 input, it's mostly IP4 rewrite, IP4 input, oops, we got to send one to ARP. Well, whoops, let's roll back 2 next, by 2. Say, okay, PI1 is going where it's supposed to go, but the other guy isn't. So now we do a little bit of juggling to actually do the right thing. These mechanics take an hour of staring at to fully believe that they work. They really, really do. But from the plumber's point of view of the universe, the game is to say that the weather tomorrow for 2 packets is the same as the weather today. Enqueue them, and then if you got it wrong, which doesn't happen real often, you just go fix it up. And there turn out to be about 3 cases. One is, it's ABA, AAB, 2 in a row to one place, and then there's ABC, which is, A is where we sent the last packet of the previous trip. B and C are just both different, and you end up kind of having to do the, kind of do the stuff. If you really unwind it, you'll see that the you'll see that the result is exactly what you want. In fact, empirically, you're not going to find packets being misdispatched. Now, the last thing in the world you actually want to do is to have everybody inlining that piece of ridiculousness. This is the sort of the seminal example of the speculative. The speculative NQ. What you see in the MacSwap sample is macro that captures all of this logic. I mean, it turns out it's not going to actually run it because of what MacSwap does, but there's a nice handy macro that encapsulates that predict false switch that says, oh, what possible mistakes could I have just made? So the gig in the dual loop is always send 2 packets where the last set of packets went and straighten it out later if you were wrong. This is Keith's,
Perfect.
Yeah, probably.
Yeah,
if it's more than yes or no, yeah.
Well, what I was wondering is how many.
Just wait till the mic comes
Give
back.
Erin a break. She's working hard for you.
I'm sorry, I
No.
can't expect you to magically appeal. No. Okay, so the question is, how many false predictions can you get away with before, you get a cache miss or a performance hit, or is this sort of like tuning that you do later on when you're running on real hardware?
At this level, you're not really tuning. The strategy is known to be pretty effective when you get reasonable trajectory locality through the graph. And it's not that, you're taking cache misses particularly, it's that it costs you thinking a little bit more about where you're pushing packets. Mostly graph nodes have one favored path, and then there might be a couple of exceptions per frame, if that. So the strategy basically, we've measured it pretty carefully. It's almost uniformly a win to do this.
Oh, so there's enough slop in the timing, even at these speeds, that you can get away with
yeah, well, you mostly win at this game so many times that unless you manage to have a graph with as many successor arcs as you have packets in the average frame, and you were populating them about evenly, would this burn you? It's almost Pareto optimal. It's not going to make anybody much worse off. And 100,000 foot, it is correct, and it in almost every case I've ever measured, it wins big enough. You just you wouldn't consider not doing it really.
So we just do the boilerplate and.
Yeah, I mean, I would strongly suggest you just, follow the pattern. The only reason for the explanation is it's kind of interesting. It's a cute trick.
Yeah.
Well, I don't know. I think it's cute. Other people may see it as as somebody sweating in the middle of July or something, but.
No.
Yep.
You need to understand that there are no smoke and mirrors.
Yeah.
Right? Because the first time I must admit, the first time I saw, and Dave explained to me, it's like, and we just assume that the last place we send a packet is where you're probably going to want it, so we're just going to send it there. Like, what? My whole rib brain just exploded because I'm so used to that constructing a absolutely consistently formed routing table, which then gets turned into a forwarding table. You can't do that. But he said, oh, slow down, fella. We don't drop any packets. We clean it up. This is what big boys call data plane programming. I went, okay, sorry, sir. I understand a bit more now. But it was a big eye-opening thing for me. That was probably the only thing I kind of went, that doesn't feel right. And I just wanted to make sure if anyone else felt that, you're just magically unicorn dusting how packets get to the next node and it will fix it up if it goes wrong, that we're trying to hide any kind of performance stuff. No, it's done in that. It gets cleaned up before it goes away.
The graph scheduler and the dispatcher are not terribly complicated, but there's a lot of details, and they're not really. If you want to build a feature, you don't actually need to go blow your head off trying to get all of these details on day one.
Yeah.
After a while, it absolutely pays to read through the stuff and convince yourself that it's right. I mean, I've convinced myself that it's right, and I haven't seen too many people complaining about it. But the truth of the matter is, it takes, frankly, this is an Elliott Dresselhaus trick that he used at NASA Ames doing finite element modeling, this sort of speculative NQ stuff. So it's a trick that has been around. There are a number of cute tricks in here that you may not have seen before. This is just one of them.
Cool.
So can I change? This is like processing 2 packets at one time.
Right.
So
Let's just get off this. This is kind of cleaning up your
I know.
next node. Do you want to stay here?
I'll go to the question.
Oh, yeah.
Can I choose 3 packets at a time?
You can. The empirical result is that for certain things, it might be worth doing three or more packets at a time. What I typically tell people to do is, look, if you get there, you're going to have a lot of trouble getting the prefetch strategy, coding the prefetch strategy. There's a whole other school of thought about building graph nodes, which is a pure pipeline, which I don't really necessarily want to go into because it's lightly used. There, what I've ended up doing is to decompose the processing into as many pipeline stages as you want, so that you can basically run until you hit a dependent read, prefetch it, and go on to another packet. It's a purely pipeline model. If you look in vnet pipeline.h, I think is the file, you'll see the infrastructure, which again uses the same stuff, although not quite in the same way, to actually push the packets forward in the graph.
Yeah, but my real question is,
Yeah.
even if like 2 is the number we go for, but if I want to write a plugin by myself, do I need to also write this type of code to handle the case when the prediction is wrong?
Plugin is really that's just a where do you find the bits kind of question. I would definitely, at least in the beginning, stick with the boilerplate, because you'll get things will work. If you one of the nastiest things you can do is enqueue the same packet twice to 2 of your friends. That really breaks its brain, and I do not want to help people debug those.
Yeah, so I think we're kind of, and I'm not trying to shut down the question, but just making sure we're not confused, right?
Yeah.
So I just want to make sure I answer his question and make sure we close that one, and it's over to you, Christian.
The answer is I can just go with this. I don't need to write the exception control by myself.
Right, there's a macro that's in there that we showed, which is the NQ validator, right?
Yeah.
And with the ×2, we're inside handling 2 packets at once,
Yeah.
which Dave wanted to show in IP as a better example of it than walking through the macro with all the if-defs, right? So that's done for you. Yeah, it's part of the standard template, that cleanup. If you're asking about changing how many things am I going to handle at once, that's a topic where we generally call adjusting the stride length. I'd rather park that to maybe a more advanced session, because if you're at that level where that's your bottleneck, you have a very specific list of issues that are pretty advanced. But so you can do it, we recommend you don't, because once that becomes your bottleneck, we can address it. Sorry, go ahead.
Yeah, my question is, I just want to confirm that as a user of the VPP, I don't need to write do I need to write the prediction?
No.
I mean, the
It's
case
right
when
there.
No,
That's
right.
That's it there.
Yeah, that's it. That macro is your friend, and even the Emacs skeleton will splat the stuff down for you. I mean, it did in this case. Yeah, although there are certainly cases in the code base, the classifier being one, where I don't exactly do this. You'd be better off, if you're just building a normal feature, not to go anywhere near trying to invent this stuff out of whole cloth. You'll save yourself a minute in aggregation, and for God's sakes, don't enqueue the same packet to 2 different places because it's guaranteed to cause a colossal cluster beep.
As a matter of fact,
I don't want to have to debug that one for people.
what we generally recommend you do is when you're developing your feature,
Yeah, is just turn off the dual looping completely.
Yep.
I just usually
While
zero and is a pretty good way of doing it.
Oh yeah, yeah.
Yeah, or if zero the whole dual loop because it just. Well,
Yeah.
my process, and I've done probably more of these than anybody, is I'll turn off the dual loop by just ifing it out, and I go get the single loop right, because you have to add a variable, yada yada yada, and then what you can do is the variables in the single loop are invariably, pardon the pun, named next zero, foo zero, blah blah blah. What you do is you pick the variable declarations up, and you have each of the zeros have a puppy called mumble1, like next one, so that once you've got the single loop coded and working correctly, then what you're doing is trying to get some performance out of it, and it's a very mechanical thing you can do while watching the ball game.
Yeah, we also have some examples like this in the PDK where we kind of work with 2 or 4 packets at a time, and maybe just a few other ideas like the times when we don't have an exact multiple of 2 packets or 4 packets. So what we could do is we could leave out those packets, like 1, 2, 3 packets, and just have a for loop that works with 2 or 4 packets at a time, and then just handle the last few packets.
Yeah,
separately.
that's exactly the way this is.
Yes. Or duplicate some of the packets, like you are, for example, missing a few packets. You will just use the last packet and clone it several times. But you have to avoid exactly what you are saying to actually do the active operation that is usually at the end, enqueue the packet. So you can prefetch the packet, you can compute whatever you need to compute on the packet. You'll do that several times for the same packet, but just make sure that at the end you are only enqueuing that packet once.
Yeah, that species of trick is used in a number of places in BPP. The one danger is if you're doing things like decrementing TTL.
Yeah, exactly. So whatever is an active operation that would actually change that packet, you cannot do it. You can do reads, you cannot do actually writes on the packet. Sometimes you can do it depending on the algorithm.
The mtry walker exactly works that way. It just sits. Once you hit a terminal leaf, if you hit, if you hit a slant 8, it's going to sit and do the same operation, 3 more times on the top ply because it just absolutely know that one.
So the basic scheme is, how much work do I have left to do? Go get my frame. How much work do I have left to do? Who do I want to send it to? How much room do they have for me to send to? And am I allowed to do it? Try and do 2 packets at once. Validate that I'm allowed to go, that this is the correct place to go send it. Macro, go sort it out, clean it up if it's wrong. Clean up any odd numbered packets, i.e. 1 packets or less than the stride length. And then tell the main loop, you've got a pending frame to go deal with, right? And that's the basic game in the basic dual while loop. Now, what we'll cover tomorrow is we'll monkey around a little bit with, remember the trace add AF packet input 10, and we saw our MacSwap in there. It didn't have a lot of really good information. There was maybe some index information, that was about it. I think what we'll do is we'll try playing around with, let's add the actual, what source MAC address came in, what destination MAC address came in, and you see in the later nodes, that's actually swapped. So we don't even have to run TCP dump, Wireshark, what have you. The next node says, here's the MAC address I got for source, here's the MAC address I got for dest, and we can tell it, here's the MAC that we got in to MacSwap, so we'll monkey around with that. So now just want to open it up to questions. It's probably a little late in the day, start hacking around on code, make install, that kind of thing. We'll hit that first thing in the morning. We're going to mess around with the CLI, the API, as I mentioned, trace, and then any other questions. There's probably a few other things I had on the agenda to cover in the morning as well, specifically to do with this. And then we're going to cover the buffer metadata, some of the multi-core stuff and DPDK in a bit more detail after lunch. So with that, any questions before we wrap it up for the day? Yes, Jeff.
I have a easy one. What's with the code style, the curly braces in weird places?
It's you know, it's basically the GNU, you know, GNU standard, you know,
Oh,
in
that's-
Emacs
okay.
it's MetaX, you know, GNU.
I knew that was the answer. I just
Yeah.
wanted
Well-
to hear that. Yeah.
Yeah.
But it's not really enforced, right?
Yeah, and yeah, I'm not the local white space policeman. I'd appreciate it if you go work on some file. If you please don't run it over with a white space lawnmower, because you know, damn, then it's really hard to review the diffs. And you know, we've been reasonably disciplined about it. Although you're going to see places that use, you know, to be frank about it, more of a Cisco, you know, cuddled up bracing style, which I personally detested since the day I was hired 20 years ago. So. Oh well, that was
Just an
that was
artifact of my typing more than anything
that
else.
was no. Don't blame Keith. He was just trying to do if zero for
Yeah.
Aussies or something.
Oh, no, you see what I have to deal with on a daily basis, which is awesome. This is how I learn. Sorry?
Yeah, yeah. It's
Well, isn't the first role always to do, like when you're in France, speak French, when you're in Italy, speak
yeah. When you're in Rome, do what the Romans do. Yeah.
I think the problem I come across is there's been a couple of files where there's 2 or 3 different styles.
Oh, well, you
Clean it
know.
up.
You know, we can. I actually don't mind if folks decide, you know, I can't stand the fact that this file has, you know, N bracing styles in it. Let's do nothing except fix it in one commit, so that for God's sakes it's not mixed in with, oh, let's go see if we can, you know, invent a new species of rocket here. You know, because we'll look at it. If you promise it's just white space diffs, I'm going to say, oh, okay, I can stand this. Click done.
Yeah.
But if it's mixed with something else, it's going to just make my head explode. And ditto for the other committers. And
We
you
had
know,
a similar thing in ODL, even though it's Java. We adopted a particular template and code styling format, right? And we asked all committers or anyone contributing to use that format, and we get very trivial changes, and they did exactly the right thing. They applied the template that we asked them to. We got these humongous Gerrits, and I was like, oh my fuck, that was a stupid idea. Oh, let's hold it back. Okay, so please submit your change in any format you want, and follow it up with a subsequent, just the white formatting only change. And I got one of my guys just to go through one day and just splat, just apply massive change to the entire repo, lay it down, and then from there on, your changes must adhere to this template. And it was just a lot easier. You can't be dealing with mix of formatting changes and code changes. It's just a nightmare.
Speaking of this, can we decide if we want to use spaces or tabs, not have it mixed at the same time? If we're at
That-
religious subjects.
That's probably not something we should decide here. Maybe at the VPP meeting Tuesday morning when there's communities there, and we can have a discussion about it.
yeah.
That would be an open thing to
I mean,
discuss.
like I say, I'm an Emacs guy. Whatever Emacs does when you say meta, meta XC stat style GNU is pretty much what I'm going to do. Again, it's not a religious matter. It turns out, whatever makes Jarrett's head explode, and I don't know. Hey Ed, can we actually reconfigure Jarrett a little bit to kind of not bother us with so much white space?
It's going to basically show you anything that's changed from a Git point of view. So it's a Git diff problem. I'll look into it and see if that's possibly doable. The other thing I was actually going to strongly urge is, if any project actually does get religion about white space, please, for the love of God, figure out how to make it part of your build to check to make sure that it's done right. Because the worst thing in the world is having to review for white space. It's just ugly in every direction.
Yeah.
And you really want the build to barf. If you're going to be pedantic about it, you want the build to
Yeah,
barf.
well, being pedantic about it is sort of not in my character, but you know, to be appreciated if the stuff didn't look like it had been run through the nearest food processor, if possible. I don't know.
Pants, apart from the drapes, how's everything else look? Make sense?
Yeah.
Just one quick note, actually, for Linux kernel, for example, for their release process, they use some Perl scripts. I think it's check patch .pl, and that would check for a lot of syntactic errors, like cosmetic things. Will check for white spaces, tabs, whatever.
Yeah.
The problem is that you'll get a lot of errors, at least initially, a lot of issues, warnings, whatever that you need to fix. But there are tools to check for these things.
I went through that with the whole let's sanitize from Java 7 to Java 8. That was an enjoyable experience. Not good for a few thousand lines of code change, though. Yeah, good point. But again, this is something, by and large, the community needs to decide. Remember, you just heard Dave, there's a bit of history here, right? And if we're going to do it, let's just do it once. Any questions about the loop itself, the node itself? Yeah, we covered the registration. We covered how it gets wired in. We covered the vlib, node, runtime T. We covered how these numbers, very small integer numbers, end up getting you to the next graph node. And we covered why there's two loops. Tomorrow, as I said, we're going to mess around with trace. We're going to mess around with a few other things like the CLI and the actual binary API. So far, so good. There was a few tic-tacs earlier on with different hiccups, but thanks very much, by and large, for everyone's patience with that.
In case of tunneling, I've heard you saying you'll remove the graph nodes from the top, right, from the beginning, and then you'll roll back for tunneling packets. Let's say IPv4 comes twice.
No. Sorry, I was just trying to explain how by using MacSwap, it's very simple. We're not changing end caps on the outside, so we're not changing packet lengths and pointing into the packet, subtracting so many bytes from the top, adding so many bytes on the front, re-end capping it. We're just taking two fields and going. So we don't have to worry about all these different things and calculating CRCs and stuff like that.
Yeah, how the tunnels work, that's my question.
Oh.
Well, I dug into that recently.
Yeah. Please.
So the metadata about a packet has an index, like a pointer, which is kind of the start of the current encapsulation I'm looking at. It starts at the very start of the packet, the Ethernet frame, and when it hands it off to, say, IP input, it now points at the IP frame. When that passes it off to UDP, it now points at the UDP frame. When UDP realizes it's a VXLAN packet, passes it to VXLAN, it's now pointing at the VXLAN frame. And again, it looks at it and says, oh, there's an Ethernet frame inside, so the pointer just keeps progressing. That's how you know where you are in the encapsulation. In the decapsulation space, you start with the packet you want to encapsulate, you roll backwards, add your header, roll backwards, add your header.
Yep. Yep. And it's fair to say that the VPP buffer metadata tends to use assigned offset because it just makes that easier. The DPDK kind of goes relative from it ends up being unsigned, and I personally find that pretty unhelpful. That converting one to the other, you end up having to be careful about it. But that's a religious war I'm not going to step into.
Yes, question, Jeff.
The packet generator, is that fast enough, or is it not to be used for real things?
The packet generator is more for initial functional testing than it is for performance testing. It is reasonably fast, but it's not particularly threaded. If you want a fast packet generator, see also T-Rex or the DPDK packet generator. It's really for, I want to, here's a packet I want to inject the Ethernet input with the idea that it's going to wind its way to my new feature.
And to maybe even get close to seeing your dual loop, the outer dual loop actually do something.
Yeah, the other thing is it's very handy if you want to know that you just sent a burst of 100 packets, to do that once and then stop, so you can just fire, you can set a breakpoint in a dual loop, fire it up, and just make sure that it's doing its thing. Dual looping, honestly, once you've done a number of them, you just get where, oh, okay, I'm going to be just careful enough to get this right on the first shot. The first time it compiles, it'll work, never to be heard from again. But it is a little bit of a you have to be careful about it because you try to sort of mix stuff into ice cream. You get a mess if you're not careful about it.